All right, let's continue our work in example 2. So now we're going to look at the next page with part C through F. So on the next page, we just have a copy of the function f and the graph and table from the previous page. So what I'd first like you to do is to copy your work down from the previous page. So I'll fill it in here to give you a chance to also fill it in. 0, 0, 1, 1, negative 0.5, negative 1, negative 0.5, 1, and 3. And I'm going to plot my points. And feel free to pause the video if you need some more time to fill these in. All right, now let's take a look at part C. So part C says, on what intervals is a of x increasing or decreasing? So let's break this down into each case. So increasing. So recall a prime of x is equal to f of x. And now, how does the derivative of function tell us about the original function? Well, recall from Calc 1 that if a derivative, so if a prime of x is positive, then our original function, a, is increasing. And just while we're here, let's talk about when the derivative or when the slopes of a function are less than 0 or negative, that means our original function is decreasing. And I know we've been talking about antiderivatives quite a bit, so it's really important to pause here if you'd like to meditate on this relationship that we learned a lot about last quarter or in your last Calc 1 class. But it's maybe been a while, so it's okay to review it and think it through here. But so the sign of the derivative tells us about the behavior of the original function. So because a prime, the derivative of a, is equal to f, we can learn about if our function is increasing or decreasing based on the sign of f. So to determine increasing, we need to look for when our derivative, which let's just recall to really bring it home, which is f of x, is positive. So where is f of x positive? We see that f of x is positive along this part of the graph and this part of the graph. So what are those intervals? Well, f of x, which is the derivative, is positive on the interval from 0 to 1.5 and from 4 to 7. Okay, so now let's look at decreasing. So we already talked about when this should happen. Well, decreasing, our derivative of the function is equal to f. So decreasing, we're looking for when that function is less than 0. So the intervals on which our function is less than 0 happen when our function f is negative. So that happens on the interval from 1.5 to 4. So now let's take a look at part D. And so just recall, we've just done in part C, just to really bring this home, we found where the function a is increasing and where the function a is decreasing. Okay. So then part D asks, at what points does a of x have a local max or a local min? So recall, what does that look like? Well, if a of x has a local max, we look like this. If a of x has a local min, we look like this. So then what happens about the derivatives there? Well, if we look at the slopes of tangent lines, the derivatives go from positive to negative. So at a local max, the derivative, which is f of x, goes from positive to negative. So we can check where f of x has a 0, and then check the sign of f of x on either side. Similar case for a local max. Here now the derivative would go from negative to positive. But to actually find the test values or the possible mins and max, we need to find where the derivative of a is 0. So to find possible min maxes, find or check where the derivative, which is f of x, is equal to 0. Okay, so where does that occur here? I'm going to change my color to red to emphasize that we're looking for the zeros. So we're 0 here, we're 0 here, and here. So now what we want to do is look at either side of those zeros. So the first part here, f goes from 0 to plus. So we do not have a local max or min here because we don't change sign in that derivative. Okay, what about this next 0? We go from plus to minus. So our derivative is positive first and then minus. So we have a local max here. Now, what about this 0? Well, our derivative, which is f, goes from negative to positive. So we're looking at negative slopes to positive slopes. So here we have a local min. So we know f of x is equal to 0 at, and we're just going to use 1.5 at x equals 1.5 and x equals 4. And we check that f goes from positive to negative at 1.5, which means x equals 1.5 is a local max. Clear some room here. And f of x goes from negative to positive at x equals 4. So x equals 4 is a local min. So just highlight our summary here. X equals 0.5 is a local min. X equals 0.8, x equals 4 is a local max. Okay, nice work. All right, let's now take a look at part E. I'm going to clean this up a little bit, so make sure you have this all filled out in your notes. I just want to make sure I have enough room for the remainder of the problems. Okay, so part E says, on what intervals is a of x concave up or concave down? So recall that to determine concavity of a function, we usually look at the second derivative. The second derivative is positive, then we have concave up. And if the second derivative is negative, then we have concave down. So we don't have the second derivative, though we could compute the derivative of f by looking at our function f. But we can also read or interpret what this second derivative sign means. So if the second derivative is positive, that means that when we had the derivative, we were increasing. I'm going to add some more equivalencies here. So concave up, or the second derivative being positive, means that our derivative is increasing. And concave down, second derivative being negative, means that the derivative was decreasing. So let's take a look at the derivative, which is f, and check where is this function increasing or decreasing. All right, so here's our function f. Let's first look at increasing. We see that our function is increasing along here. then it decreases. So decreasing, decreasing along this interval, then increases here, and then remains constant. So here we just have a 0 derivative. So it doesn't tell us about concavity. All right, and we can kind of think through why the derivatives of f, or the second derivative of a, is going to be positive here. We drew some lines. We see the slope is positive. Here, negative. Here, positive. Okay, so we've identified where the function, or where the derivative, is increasing or decreasing. So now this can tell us about concavity. So we see that we are concave up. And more specifically, a of x is concave up on the interval from 0 to 1. And again, on the interval 2 to 6. And a of x is concave down on the interval from 1 to 2, where our function f is decreasing. Concave up and concave down. All right, now to part F. So part F says, use your responses above to sketch a more accurate graph of a of x on the blank axes provided. So again, so far, what we've plotted are just the points, or points of a of x at whole numbers. But what we have in C, D, and E are more descriptions about the behavior of what happens with a of x in between these points. One thing I want to point out is that in part D, we learned that at the point x equals 0.5, we have a local max. So we haven't graphed the point x equals 1.5, or a of 1.5. So we don't know how high this max is. So why don't we first calculate that maximum value so we get a sense of a local maximum of our function. So kind of a first step, let's look at a of 1.5. So a of 1.5 is going to be the integral from -1 to 1.5 of f of t dt, which is equal to the integral from -1 to 1 f of t dt, plus the integral from 1 to 1.5 of f of t dt. So now the integral from -1 to 1, we know that is just a of 1, which we can find from our table. So all we need to compute from our graph is the integral from 1 to 1.5 of f of t. So let's look at that. So we need to compute this integral, or the area under our curve from 1 to 1.5. So it's going to be the area of this triangle, where we've seen the base is 1/2 and the height is 2. So the area is going to be 1/2 times base times height. So let's write that out. So a of 1 is 1. So this becomes 1 plus 1/2, 1/2, 2. So this is equal to 1 plus 1/2, because a 2 cancels with a 1/2, which is equal to 1.5, or 1.5. So let's go ahead and plot that point, 1.5, 1.5, on our graph. So we see at 1.5, our output value is 1.5. So it sits right there. Okay, so now let's start drawing the sketch, or the curve of our graph connecting these points. So again, we can look at the function f, at the area under this function, to give us some insight. And we can also look at the work that we've done in these parts. Okay, so if we just consider this first section of our graph from -1 to 1, or -1 to 0, rather, we see that there's no area accumulating on our function f. So how we're going to connect these 2 points is just via a straight line along 0. Nothing interesting is happening. But what about this interval between 0 and 1? Well, let's look at the concavity of our graph on those values, or at those points. Well, what we've computed is that our graph is concave up from 0 to 1. So how should I connect these 2 points? Well, I need to use a concave up curve. Okay, what about the next part of my graph from 1 to 1.5 or 1 to 2, so along this area? Well, here, if we again look at concavity, we see their graph is concave down from 1 to 2. So it'll look something like this. And then we can continue. So we know that our graph is going to be concave up, again, all the way from 2 to 6. So that means I need to draw these curves all with a concave down look. So now we're on to connecting the last 2 points of our graph, and that's between 6 and 7, or x is 6 and x is 7. So we can see that we don't have a concave up or a concave down listed on that interval because the derivative of f, or a second derivative, is 0 there. So whenever we're in the situation where we don't have concavity, that means we must have a linear function. So then we connect our 2 points with a line. And we can see that when we look at the area, or as we accumulate area along this part of our graph, as we move over a little bit, we get the same little bit of area change. So our graph should be linear there. So if we smooth things out, our graph should have a shape like this. So we've now reached the end of our video, but I'd like you to take a minute to review your work, take a look at everything you've written down, and just confirm, convince yourself, meditate on these ideas that this curve that we drew for a of x does in fact show us the antiderivative of f. Awesome work, everyone.